catch that.
So what can I help you with?
First problem of the day.
I can't help me with that. I have some ideas, but I don't know. That's just general stuff to help trigger memories if they keep triggering.
Can you go over the difference between like the lossless and lossy? What the differences was between those two?
Yeah, for just for plane wave materials.
Yeah.
Yep. So first test is loss tangent, which is sigma over omega epsilon. And if that's a lot less than 1, which practically means less than 0.01, so it's got to be 2 orders of magnitude, then we'll call it lossless. And if it's greater than 1 by, again, practically, if it's greater than about 100, then we'll call it high loss. If you're stuck in the middle, then you've got to use the long forms. And regardless, the two things that you usually need are gamma and eta. Okay. So if it's lossless, then alpha equals 0, beta is omega root mu epsilon, and eta is root mu over epsilon. And these two you can sort of cheat. It's not really cheating, but it spares you a certain amount of calculator pushing. Fixing by root epsilon. I think I told you this happens. This is the same as n. This is the index of refraction. So that's lossless. The book has or one of the books, not this one, has a low loss, but I won't bother with that. If this is the case, then you just disregard. And that, by the way, means the thickness of eta is 0 for all practical purposes. High loss, then you can use the approximation that sigma is essentially infinity. So that term is a lot bigger than that term. We'll blow that off, which leaves you then the gamma is the square root of j omega mu sigma, or alpha equals beta equals root omega mu sigma over 2. And as far as writing things on cards, you can just write that down and do that approximating yourself, or you can write this thing down. Eta then comes out to, the magnitude of eta would be root omega mu over sigma. Because again, this term goes over. And the angle is the square root of j, so theta sub eta is 45 degrees, and the loss tangent, or loss angle rather, is 90 degrees, which is the inverse of that. So what we're saying is if this thing is bigger than 100, let's call it infinity. If you're stuck in between, then it really depends on your calculator whether this is all you have on your card and you let it figure out the real imaginary terms, or you use the long form. So if sigma over omega epsilon is greater than 0.01 or less than 100, alpha is omega root epsilon over 2. Beta looks very close to that. And eta is root mu over epsilon over the fourth root 1 plus sigma over omega epsilon squared. And the angle is 1/2 the inverse tangent of sigma over omega epsilon. Okay? But if you're good enough with your calculator that you put all that in with the j's and you break out the real and imaginary parts for you. And you can always use that, in fact. You don't have to use the approximation. If I say, here's this material, find me something like skin depth, the first thing you're going to do is test. And then if you want to use the approximations, you tell me, this is a low loss medium. Low loss tangent is less than 0.1. I'm going to treat it as lossless. It does the skin depth thing. And just make sure you write on the, if you use an approximation, just write down why you're using it.
Just to make sure, we get one sheet that's like the last sentence.
Yes,
Right.
one side of one piece of paper. I think that's more than enough for you to lose the equations that you need to find. No magnifying glasses. And don't forget epsilon naught and mu naught. It's stored somewhere. I put epsilon naught on a recall 8 on the calculator, so just, it's a real pain to touch into that, but otherwise that's an
That's omega times, right? For like alpha and beta? Or is that?
Yeah, that's an
the
omega.
root of
No, it's not the
omega?
omega root. No, it's omega times the square root of. Yes, but this is the fourth root. It's not 4 times the square root. And those three are rather difficult to I don't know, I've tried myself to derive them, it's not easy. So if you want to use the long ones, you should have them, and you should know where the omegas are. It's a square. It's easy to forget, does this go inside the bracket or not? I can know that. I suppose while we're at it, the other things that are relevant here are the reflection coefficient. The transmission coefficient. And those could be complex if beta is complex. And then power. Forgot the E to that. Power density. And that's 1 half E cross H complex conjugate. So if you want to do it that way, you can. And this is obviously the direction of propagation. So it could be X. Wait. But that's a good thing to have rather than have to go back to derive E cross H, which could take a while. It's not a bad idea to have. Things like, well, what's the loss of power in dB after it's gone X many, X bar? That's this thing. And you don't need all the rest of it. You just need that number. Ratio over distance over distance.
Is that, or maybe after the P?
P average.
Oh, average.
Sorry. Yeah. The time average, as opposed to the instant. In time. E of Z and T, some magnitude. This is the polarization. Direction of E. This is the wave number. Or the it's one over wave one. What's the other number? Propagation. If alpha. Alpha is the attenuation constant. Omega is the frequency. Z is the direction of actually these two together. Z and the sign give you the direction of propagation. Remember, if that's negative, it's going in the plus Z direction. Okay. And E mod is the magnitude, and the magnitude of H is E over magnitude of eta, and the eta term, the angle of eta turns up in here. Theta of eta is the lag angle from E. Presumably you have written down something like that. That's pretty much plane waves. As far as equation. Oh, phase constant. That's it. Gamma is the full That's the propagation. And eta is the intrinsic. And I can do it either way. Give you the symbol or the name. I expect you to associate those. Simplifications for good conductors and good dielectrics, that's what this is. This is a good dielectric, that's a good conductor. And that's all that I want to know. And how to tell whether the simplification is valid is the loss tension. Skin depth is 1 over alpha. Takes 5 skin depths to get to 0. And resistance of a given geometry, the resistance would be it's still rho L over A for ordinary conductors, but the area is only 1 skin depth. You assume that the current is actually flowing only in the unit stuff. In actuality, of course, it's dropping off like this. But what we're arguing is that this area is the same as that. Total current, if you only go in 1 delta, is the same as 1 delta. It works reasonably well for approximations, and it's very good for resistance. Don't worry about dielectric loss. That power thing is effectively the Poynting vector, and you should know it's E cross H. Oh, what does the Poynting vector mean? I did that derivation, and I don't expect you to redo the derivation, but if I gave you that equation, can I take these off? No. D by dt. That's not something you need on your sheet, but if I gave it to you, would you tell me what it means? The easiest way to figure it is by units. So electric field is like volts. Sigma is Siemens, which is 1 over ohms. And I think I put the sigma in ohms. No. Units of mu, Henrys per meter. And the units of epsilon is farads. There's another meter here, and that's per meter. So what are those terms?
Power?
Power. 3 different kinds of power. Power consumed by a resistor. A squared over R. d by dt, time derivative of the energy stored in an inductor, Li squared. And the power again, d by dt is the energy stored in a cap. And then the per meter cubed says the whole thing is a volume. So that says that what this is a measure of the power sunk in the volume. And the volume looks like a resistor and an inductor based on its electrical properties. The volume being whatever you're beaming your RF signal into. The air around yourself. It's helpful that way to distinguish from this is conductive loss, and these are energy storage things. Impedance comes in ohms, but it isn't a loss impedance. Your cell phone sends that signal out. It's not like the signal gets absorbed by the air and gets to the other end, but from the perspective of your cell phone, it's gone. You have to put energy in the physical discharge that. It goes into the LC circuit that is the world. From the perspective of me. Anything else on wave stuff?
Reflection, is that anything going to be a reflection of the plane wave?
Yes, I'll do this normal incidence. I will not do oblique incidence. So you should know gamma and tau. You should know how to figure out what percent of the wave is reflected, what percent is transmitted. So questions like that last one problem when you've got a beam of impacting a tissue, what percent gets in, and then that can go on from there. Once it's in, how deep does it go? So then get scanned back. So you have EI. Then ER would be EI mod gamma. And ET would be EI mod tau. The transmitted H goes in the second medium, so you got to remember there's something squared in it. So P reflected would be EI naught squared, gamma squared. You still have 2, and it's all E to 1. Right? We'll assume that that's how you do it. Then there's the angles, the alpha and the 8 beta signal. But for the power transmitted, still have EI naught squared and tau squared, but the medium is different now, so this is an 8 to 2. That's an easy one to forget. And then you had better hope that the incident power is equal to the transmitted plus the reflected. If there is a decay term here, e to the minus 2, it would be alpha 2, z and cosine theta sub theta. It's not usual to, normally we assume you're going from a lossless medium into a lossy. So it doesn't always figure on the reflection side, but it could. The only kind of standing wave stuff I'm going to ask you, I'm not going to ask you things like, all right, so we got the standing wave, how far back is the first null? We didn't have time to cover that. But what is the reflection coefficient for a perfect conductor? Well, if it's a perfect conductor, then sigma is large, and if I erase that now. So eta for a good conductor over sigma, but sigma's really big, this is going to approach 0. So A to 2 is 0. So gamma is -1. So all of the wave is reflected off the perfect unit. That kind of leads on 1 to 2. And it makes a fair question to ask, well, how do microwaves work? Microwave oven? I mean, isn't the point that the food is a conductor? It's not perfect. You get a lot of this stuff. It's not perfect. Approximation won't work. I won't get any energy in my hot water. Other question? That at least gives you the sort of base equations for the plane wave stuff. Not worrying about Snell's law or anything like that. Phasers. I think that I would not assume that everybody did real well on phasers and time domain on the last test, so I'll probably do that again. So give me this equation in both time domain and frequency domain forms, so get that right. A couple of questions there. Why was Maxwell's displacement current not easily verified? What is displacement current anyway? How do you write the four equations in plain English? Those are all fair game. And then moving object questions. Probably another one of the loop next to the wire. Nothing else, those are